Good morning, everyone. So, next practical that we are going to start is the determination of pA2 value by Schilds plot method. Okay. So, the purpose of today's experiment is that the student shall be able to know about what is pA2 value, then its use in the experimental pharmacology. Then know about determination and calculation of pA2 value. Then know the pharmacology of the drug, that is prazosin. This we have already seen that what prazosin does, in which condition it is being used, and to which class it belongs to. Then know the procedure of rat anacococcygeus muscle preparation. Okay. So, terminology, that first of all we will define the term, that is pA2 value. Okay, so pA2 value, just like that of the pH, it is defined as negative logarithm of molar concentration of the antagonist, which is required to reduce the effect of double dose of agonist to that of a single dose in absence of antagonist. Okay, so in very simple words, I would like to tell you that what pA2 value is. So it is basically talks about the antagonist concentration which is required to bring down the response height of the double the concentration of the agonist when we compare it with that of the uh, normal or 1 unit concentration of the agonist in absence of antagonist. So what I mean is that, so it actually defines that the concentration of antagonist which is required to halve the response height of the double dose of agonist. Okay, so double dose means what? Consider one example. We have drawn the DRC of agonist and we selected two doses. That is, one dose is zero point 0.4 and another dose is zero point 0.8. So if you compare these two doses, so compare it as A, uh, consider it as A, zero point 0.4 as A and zero point 0.8 as 2A. Okay, so what this pA2 value is, that suppose the response height of zero point 0.4 ml of the agonist dose is suppose like 16 mm. Okay, so let's just assume it is 16 mm, and that of 0.8 mm it is something about 28 mm. Okay, so according to the pA2 value, we determine the concentration of the antagonist which is required to bring this response height of zero point 0.8 to this, that is 16 mm. Okay, in presence of antagonist. So in this case, this 16 mm value which we have got, it is in absence of the antagonist. And what we are doing, that we have selected a double the dose of the standard, and we will be increasing the dose of antagonist, and then we will plot a graph, and onto the graph what we will do, we will get a graph something like this. Okay, we will get a graph something like this, and we will plot the points which we will get the responses over here on this particular graph, and we will extra interpolate this 50% from over here. On this y-axis we will have percent response height, and on the x-axis we will have the log dose. Okay, so it will be negative logarithm. Okay, so this 50% of it will we will interpolate on this particular line, and then we will extrapolate on this line. So whatever value we will get, it is nothing but the pA2 value. So why we have selected 50%? Because we want to have the response height of the double dose of the standard, so that we will get the original standard response height, and we are trying to find out at which concentration of antagonist it happens. Okay, so this particular method, that is pA2 value, it helps us to determine whether the antagonist is competitive or it is non-competitive. So that particular point we will be studying in further slides. Okay, so let's just move forward so that you will get more understanding of the things. Okay, so description: studying the bioassay of antagonists is important part of experimental pharmacology, like the bioassay of agonist. So we have studied bioassay of agonist earlier on, of the serotonin, of the histamine, as well as you have studied about acetylcholine in last semester. But this semester we will be studying about antagonist bioassay. Okay, so antagonist, it may be defined as an agent which prevents the action of an agonist on a receptor or the subsequent response, but it does not have any effect on its own. So it does have the affinity towards the receptor, but it doesn't have any kind of intrinsic activity. That's how we can differentiate between the agonist and antagonist. Okay, so depending on mechanism involved, antagonism may be physical antagonism, chemical antagonism, physiological or functional antagonism, and receptor antagonism, which may be classified further as the competitive antagonism or non-competitive antagonism. Okay, so antagonists, they have no effect of their own, hence their activity may be studied experimentally by intensity to block the agonist activity. So understand this very clearly. In case of bioassay of antagonist, we need to have an agonist in that particular study design. Okay, unlike that of the bioassay of agonist, where we will only have the agonist, we won't have any other drug. But in case of antagonist, we have to have the agonist in our study design. And why we need to have agonist? Because we will compare at what potency levels the antagonist can block the actions of the agonist. Okay, so to study the bioassay of antagonist, the response of agonist is obtained first. Thereafter, percent inhibition of the response is determined by using different doses of antagonist. So to make the graph more linear, percentage inhibition may convert into the Probit scale against the log dose. Okay, so why we convert this percentage inhibition into Probit scale? In order to make the graph more linear. Okay, so try to find out what is this Probit scale. Okay, so commonly used methods to study the competitive antagonism activity are: first one is parallel shift of DRC, second is double reciprocal plot of Lineweaver and Burke, and the third method, that is Schilds plot method of the pA2 values. Okay, so the third method, that is Schilds plot method, it is our concern method today. The other two methods, if we get a time in future, we will study about them, but today's focus will be only on the Schilds plot method. Okay, so Let us see what is this Schilds plot method. So the scientist, that is H.O. Schild, in 1947 proposed a pA scale as an analogous to that of the pH scale. So everybody knows about pH scale. So on that platform only he proposed a pH scale, and this pH scale is used to determine the drug antagonism. So he defined the pA as negative logarithm to the base of 10 of the molar concentration of an antagonist, which will reduce the effects of multiple dose X, usually 2 or 10, of an active drug to that of the single dose. Okay, so this definition we have already seen, but something is new over here. That is, here they have mentioned the X can have the value that is 2 or 10. So when X has value 2, we call it as pA2 value, and when X has the value that is 10, we call it as pA10 value. So what is this pA2 and pA10 value? We will be studying in next few slides. Okay. So example is given to explain what we exactly mean by the pA2 value. Okay. So if the presence of molar concentration of 10 raised to minus 9.4 mepyramine in the bath reduces effect of 2 micrograms of the histamine on the guinea pig ileum to that produced by 1 microgram in the absence of mepyramine. The pA2 value of mepyramine for histamine on guinea pig ileum is 9.4. So what it means that mepyramine over here, it is an antagonist, and histamine, it is an agonist. So what we are saying that if this concentration of the mepyramine is able to reduce the effect of 2 micrograms of histamine equivalent to the response produced by 1 microgram of histamine, then we can definitely say that pA2 of mepyramine, it is 9.4. So how it is 9.4? Understand the definition. It is negative logarithm. So this negative signs, it comes from this definition. Okay, and to the base 10. So this is the base 10. Okay, so when we talk about pA2 value, we have to take into account this negative value as the base as well as the base 10. So value over here becomes the 9.4. Okay, so that was the example. So a method of testing competitive or non-competitive nature of an antagonist is to determine both pA2 and pA10 values for the agonist and antagonist pair on the same tissue. So simple, it is similar like this. So for pA2, it is like the effect of double the dose, we have to reduce it to the single dose. So in case of pA10, it is 10 times of the dose, we are reducing it to the single dose. Okay, so it is only the value. Okay, so once we carry out these both experiments on the same tissue, if we found that the difference between these two values is 0.95 or very near, that is 0.8 or 1.2, then the antagonism is likely to be of competitive type. Otherwise, if the values they lie beyond this range, that is 0.8 to 1.2, then the type of antagonism, it is non-competitive type. Okay, so antagonist acting on the same receptor will have same pAx value in all the tissue or the organ preparation. This is very important sentence. What it says that if antagonist is acting on one specific receptor, same receptor, then it will have the pA value same in all tissues and organs. Okay, so objective of today's experiment is to calculate the pA2 value of prazosin using noradrenaline as an agonist in rat anacococcygeus muscle preparation. Okay, so what is prazosin? We have seen it is an alpha blocker. Okay, so as it is alpha blocker, it is an antagonist, and noradrenaline, it is an agonist. Okay, so principle of today's experiment, there are two number of anacococcygeus muscles. So if you see the name of this muscle, anacoccygeus muscle. Okay, so we are talking about coccyx over here. Okay, so this location of this muscle must be near to the coccyx. Okay, so it arises from upper coccygeal vertebrae close to one other in the midline of the pelvic cavity, and it reaches to terminal colon near the anus. Okay, so why it is given like this? With this description we are able to locate this particular muscle in the body of the rat. Okay, so anacoccygeus muscle is a thin strip of fast contracting smooth muscle. So as it is fast contracting, the contact time which we require in the time cycle will be less. Okay, so it is about 3 centimeter long, 0.5 centimeter broad. Okay, muscle is bilateral, so that two muscle preparation can be made from same animal. Okay, so anacoccygeus muscle is sensitive to noradrenaline, adrenaline, ACH, 5-HT, and adenosine, and hence usually it is used for their bioassay. So using this particular muscle, we can check the activity of any of these drugs. Okay, so we have to just replace the agonist with any of these, and we have to replace the prazosin, the antagonist, with any of the suitable antagonist, and then we can perform the pA2 value of that particular antagonist. Okay, so the competitive antagonists like prazosin and atropine, they block the contractile property of noradrenaline and the ACH respectively. So in this case, we will be using the prazosin as the antagonist and noradrenaline as the agonist. But in some other books, it is also given that instead of prazosin, they have replaced it with the atropine, and the noradrenaline, it is replaced with that of the ACH. But that experiment and this experiment, it is one and the same. If it is to be calculating, if we are calculating the pA2 value, okay, using the anacoccygeus muscle. So this muscle is densely innervated by adrenergic nervous system, where both pre and post ganglionic fibers, they are present. So the contraction of anacoccygeus muscle is through at the adrenoceptors. So prazosin is selective alpha 1 adrenoceptor blocker. Okay. So potencies of competitive antagonists, they are generally expressed as pAx values. The pAx values, they are defined as negative logarithm of molar concentration of antagonist required to reduce the effect of multiple dose of the agonist to that of the single dose in the absence of antagonist. So this definition we have studied. So higher the pAx value, more potent is the antagonist. So this sentence is very important. So if pAx value is more, then more potent is the antagonist. So we can try out different antagonist and we can compare the pAx value for each of the antagonist, and we can arrange these antagonists as per their potencies. Okay, so determination of pA2 value, that is x is equal to 2, and pA10 value, that is x is equal to 10. These values, they have wider application when we compare to the other pAx value. Okay, so requirements, the animal which we require is rat, whose weight should be between 180 to 200 gram, and the tissue which we will be isolating, that is rat anococcygeus muscle, and the drugs which we will be using, that is noradrenaline, whose molecular weight is 169.18, then prazosin, whose molecular weight is 383.401. So why we require molecular weight to be mentioned? In order to prepare the stock solution, we require molecular weights. Okay, then PSS, we will be using Krebs solution. Then equipments, chymograph with drum and smoke paper. So we don't use smoke paper, instead of it we use the white paper. So students organ bath, isotonic frontal writing lever, then aerator with aeration tube, and the other accessories. So other things that we require, that is tuberculin syringe, beaker, stopwatch, petri dish, dissection box, suturing needle, and the thread. Okay, so procedure. So first of all, we have to prepare the stock solution of the Krebs, and also standard stock solution of the noradrenaline, whose concentration should be 1 milligram per ml, and of prazosin, same concentration, that is 1 milligram per ml. So we have to sacrifice the rat by stunning on the head and the carotid bleeding. So we have to fix the animal onto the dissection board by tying its legs. So we have to open the abdomen and pelvic region by a small horizontal cut followed by vertical midline incision. So we have to trace the root of the rectum interiorly, and we have to identify two thin strips of the anococcygeus muscle which arises from the coccygeal vertebrae and reaches to the terminal colon near the anus. So we have to cut the terminal colon about 3 mm from the anus and carefully clear the delicate connective tissue until anococcygeus muscle comes into view. So we have to isolate the two anococcygeus muscles and immediately place it in the petri dish which contains aerated lukewarm Krebs solution. So this particular link, it's of the video where they have shown how to isolate the anococcygeus muscle in the main rat. Okay, so you can click on to this link and it will redirect you to the YouTube where you can watch the video. Okay, so we have to mount the preparation in inner organ bath which contains Krebs solution, that is 20 ml, and it is to be maintained at 37 degrees centigrade. So we have to tie the bottom end of the muscle to the hook of aeration tube and upper end to the isotonic frontal lever by the thread. So it is all normal procedure. That's why I'm just reading it. So adjust the magnification of responses to 7 to 10 folds. This magnification value is important. So aerate the tissue with oxygen or the carbonium slowly. So that is 40 to 60 bubbles per minute. So stabilize the tissue for the 30 minutes by applying a tension of 1 gram weight attached to the liver, during which wash the tissue with fresh Krebs solution once every 10 minutes. Like 3 washings we have to give. So we have to use a 5-minute time cycle with a contact time of 60 seconds for recording the contraction dependent responses of tissue due to noradrenaline on the smoke drum as per the following schedule. So at 0 second we have to remove the weight, start the drum and record the baseline for 30 seconds. So at 30 seconds we have to add noradrenaline to the inner bath and record the response for the 60-second contact time. So at 90 seconds we have to stop the drum, add the weight and wash the inner tube. So at 180 seconds we have to give the second wash. At 300 seconds we have to give the third wash. We have to remove the weight and again start the drum and get the baseline. Okay, So next is record the graded response of the noradrenaline in geometric progression on the rat anacophageous muscle preparation till getting the maximal effect. So we have to get the DRC of noradrenaline. So we have to select two doses of noradrenaline from the linear range of the DRC. That is, one we have to consider as A and another as 2A, bearing the dose ratio and eliciting a submaximal responses, that is R1 and R2. So understand, we have said that submaximal responses. So whenever we will be selecting the dose, we should not be selecting the dose which gives us the maximum response. We have to select the dose which is earlier to it. So if suppose 3.2 ml of the noradrenaline gives us maximum response, we have to select 1.6 ml and the 0.8 ml. So 0.8 ml here, we can call it as A and the 1.6 ml as the 2A, and the response height of this 0.8 ml will be considered as R1 and the response height of 1.6 will be considered as R2. So consider the response R2 due to the double the dose of noradrenaline 2A as the 100%. So we have to determine corresponding percentage of response, that is Ri, for the single dose of the noradrenaline. Okay, so we have to standardize the tissue with dose of 2A. The tissue is said to be standardized if it responds equally to the same concentration. That means during the drawing the DRC of the noradrenaline, whatever response height we got with the 2A dose, same or similar response height we should get after once we start with the standardization of the tissue. Okay, so we have to add prazosin, 10 times lesser concentration than 2A dose of the noradrenaline, and we have to consider it as the B1 to the inner bath which contains PSS, and we have to irrigate the tissue for 5 minutes. Okay, so we have to then record the response of the 2A in presence of prazosin, and percentage inhibition of response is determined. So what this irrigation of the tissue means is that before we actually take the response height of the noradrenaline, we have to keep the tissue in contact with the prazosin. And how to do that? We have to replace the reservoir bottle which contains PSS plus prazosin added to it. Okay, and through that PSS we have to introduce the prazosin into the organ tube, and we have to keep the tissue in contact with the prazosin for 5 minutes. And once 5 minutes gets over, we have to record the response of the double the dose of the noradrenaline, and we have to check the percentage inhibition of the response. Okay, so we have to repeat this step to record the response of the double the dose of the noradrenaline in presence of increased molar concentrations of prazosin. So the first concentration that we have considered of prazosin, we will call it as B1. The next concentration we will call it as B2, B3, B4, etc. Okay, so we have to determine the corresponding percentage inhibition of response of the 2A in presence of different concentrations of prazosin. So we have to plot a graph which is representing negative log of molar concentration of prazosin on x-axis and the percent response to the double dose of the noradrenaline in absence and presence of the prazosin on the y-axis. So we have to read out the pA2 value for the prazosin from the graph directly. It corresponds to the percent response obtained with single dose of the noradrenaline, that is A. Okay, so we know what is the percent response which we have obtained from the single dose of noradrenaline. We have to just interpolate that value onto the linear portion of the line, and then we have to extrapolate it onto the x-axis. Okay, so pA2 value is defined as the negative log of the molar concentration of prazosin, which is required to reduce the effect of dose 2A to the A. Okay, so this is the graph which we are talking about. So this is the normal DRC which we have to consider. We have to consider take the two doses of the noradrenaline which are giving the submaximal responses, and these two doses we have to consider, we have to then give. So A followed by 2A, and A and 2A we have to give the responses, and 2A followed by B1 plus 2A we have to give. So you can see from this the response height is decreased slightly from this 2A. So again we have to give the 2A response, and then we have to try out next molar concentration of antagonist, that is B2. So again further decrease in the response height it's in. So this decrease in the percent, this response height can be seen over here. Okay, and then we have to plot this graph, and then we have to extrapolate it onto the x-axis like this. So this R1, as we have already seen, R1 represents the response height of the dose, that is A. Okay, so this percent response height we have to consider, and we have to interpolate it onto the line, and we have to extrapolate it onto the x-axis, where there is on x-axis the values are in minus log m, and this value, it represents the pA2 value. Okay, so this is the observation table. This is how we have to arrange the things. So molar concentration of noradrenaline, so A and 2A as we have selected. So molar concentrations of prazosin, as we are not using it earlier on, so that's why it is to be remain blank. So response height we get R1 and R2. So there is no question of log m. We are considering this R2 as the 100% response, and compared to this 100% we have to calculate the percent response of this A. Okay, so then we have to go on adding the B1 to B4 molar concentrations of prazosin, and this B1 should be 1/10 of this concentration of the noradrenaline. Okay, so we have to go on increasing the concentration of this prazosin from B1 to the B4. So it means that the B1 will have the least concentration of the prazosin, and B4 will have the most concentration of the prazosin. Okay, so here it is shown that A and 2A, they are the selected two doses of noradrenaline from the linear range of the DRC. R1 and R2, they are the responses of A and 2A respectively. B1, B2, B3, etc. they are increased molar concentrations of prazosin. M is molar concentration of prazosin. Okay, so inference that we have to draw from this particular experiment is that after plotting percent response of 2A dose of noradrenaline versus negative log of molar concentrations of prazosin, pA2 value is directly extrapolated through the graph, which corresponds to the percent response obtained with single dose of noradrenaline. So similarly, pA10 can also be calculated. Okay, so you should understand that whatever values we have onto the y-axis, they correspond to the percent response of the 2A dose of the noradrenaline, and whatever values we consider on the x-axis, they correspond to the negative logarithm of the molar concentrations of the prazosin. Okay, So a very simple experiment, very easy to understand. So that was all from my side. So herewith I will conclude my today's practical. Thank you.